In this video, we are going to explore the concept of vectors, what they are, what use they are to us, because they are of a lot of use in physics. If this is difficult at first, you are in good company. A lot of people struggle a lot with the idea of vectors, but we are going to do our best. So here we go. A vector is a quantity. That is something that we can measure with numbers. And it has both, it's good that I can English, which has magnitude, that is size, and direction. Alright, so I'm going to draw a picture of what that looks like here. If we could find, here we go, let's grab another color. So here's a vector. This could say be a position vector. We know that it's position because we're using x and it has the little arrow over the top, meaning that it's a vector. So what do we mean by magnitude and direction? Well, the magnitude runs from here to here, so we could say, look, that's 10 meters. Alright, so there's the magnitude portion. It's pretty straightforward. This is basically to point out that even though a vector looks like a ray, it is not actually a ray. A ray goes on forever. A vector has a defined length. So if we try to draw the same vector over here, we can discuss what we mean by direction. So if we throw in some dotted lines here, there is some angle there. That looks to be about 20 degrees by my measure. That is the direction, 20 degrees. So to completely define this vector, we would say the position is 10 meters at 20 degrees. So there is your basic idea. We have a whole bunch of these things. So, for example, position is a vector. Velocity is a vector. Acceleration is a vector. We will get to it later, but force is a vector. Distance, not a vector. Let's go back to black here. Try to write a little more neatly. Distance is not. Speed is not a vector. Mass is not a vector. These are things that are just numbers. Distance, speed, mass, those are just numbers. Position, velocity, acceleration, and force are numbers that also have direction associated with them. Alright, so the next idea here. A vector, because it is a little more complicated than just a number, has some parts. Okay, so if we're talking about this vector, we can think of this, if we put our origin down here and say, look, there's 0, 0, there's our origin. Then out here we have some point, if it'll let me write, that'd be awesome, some point here, which is x, y, which is the end of the vector, right? What that means is that we could follow this thing out to the right, a distance x, and then follow it up a distance y, and we would find our way to the end of our vector. We notice some key features here. That's a right angle. This is the angle associated with our vector, and here we have our magnitude, would be the length of this side. So this would be our magnitude up here. These two vectors, because notice these are vectors, x and y, they're vectors in and of themselves. They're perpendicular to each other, and they're the pieces of our original vector. We call these things components. These things are components, that is, two vectors which are perpendicular to each other but add to the original vector. And here we can see them. We have vector x, vector y, those two adding together. Follow the x, then follow the y, and you will have made your way from the beginning to the ending. Okay, so we could say, we'll call this vector A, say. Vector A is equivalent to vector x plus vector y, and because vector x and vector y are perpendicular to one another, we can say that they are component vectors. Well, it would be nice if we could figure out how to find those components. So I'm going to draw this picture again. So here's A. I'm actually going to introduce a new piece of notation here. Here are our components, and we can label these things this way. A sub x, that is the component of A that is along the x-axis, and A sub y, that is the component of A along the y-axis. There's a right angle. There's some other angle. Notice that this is a right triangle. A right triangle. When you draw in components, you are always drawing a right triangle, which means that our old friend sine, cosine, and tangent can come into play. So, as a quick refresher here, the sine of an angle is equal to the opposite over the hypotenuse. So in this case, if we're interested in that angle, theta, we could say that sine of theta is equal to the opposite side, AY, over the hypotenuse, which is A. We should realize that we're talking about magnitudes here. That is, how long are they? Okay, so sine gives us the relationship of the lengths of these sides. So we can rewrite this to say, look, the magnitude of AY is the magnitude of A, the original vector, times the sine of the angle, or the direction. And we could then do the exact same thing with the other component, except we would be talking about the cosine of the angle, because the cosine of the angle is the adjacent side divided by the hypotenuse. I'm going to leave out the magnitudes because it makes it a little bit messy. But there you have it. So to summarize there, how do you find components? Finding components. Okay. Step 1, draw the original vector. Label it. So there are axes here. I'm going to draw on the axes. Here are the axes. So here's the angle that we're interested in, the direction of the arrow. Get a nice brown here, there we go. We then draw in the components, which are basically the coordinates of the endpoint. So start at the beginning of the vector here, go directly along the x-axis all the way out until you get to the end of the vector. Label that's AX. Then go up from that point. Didn't mean to do that. Up from that point to the end of the vector so that we form a right angle. That is AY. We can then apply sine and cosine, so we find that AY is equal to A sine theta, AX is equal to A cosine theta. And if you really wanted to or had some situation come up, we can also deal with the tangent of theta would be the opposite side, AY over AX, where AY and AX are the components. So if you just knew one component and the angle, you could find the other component, just using right triangle trig. Alright, so what about a situation where we know the components, but not the vector itself? What do we do? Well, we'd like to know the original vector. So let's say we know that AX is equal to 4, and we know that AY is equal to negative 2. And just for ease of use, we'll talk about these being position vectors, even though this generalizes to whatever. Step 1, draw the picture. AX, 4 meters, assuming positive, is to the right. AY is negative 2 meters, down, assuming up is positive. I draw the components, one followed by the other, so that they meet head to tail, so that they are at a right angle. The original vector then goes from the beginning of the first to the end of the second, so there's vector A. Well, this looks a lot like a right triangle. How are we going to find the magnitude, that is the length of A? Well, we go to our old friend Pythagorean theorem. A squared plus B squared is C squared. A can be 4 meters squared plus negative 2 meters squared. 16 plus 4 is 20 squared. So A is equal to the square root of 20. You would pick up a calculator and reduce that thing. But we're not done yet. A vector has two parts. It has a magnitude and a direction. So far all we have is the magnitude. There's the magnitude. We need to know this angle as well. So here we're going to step back into our trig. I'm going to erase a little bit so I have some space to work here. Really need that to be bigger. There we go. There we go. Erase this stuff. Okay, we know we were given these two sides. Those are the opposite side and the adjacent side. I'm looking for the angle. Well, there exists a trig function that relates those things. It's called tangent. Tangent of the angle gives us the opposite side over the adjacent side. Meters and meters. And at this point you need to pick up a calculator and actually figure out what this is. We have to solve for theta. Well, the way you undo a tangent is using what is called an arctangent or inverse tangent. So writing this thing out, we're going to take the arctangent of tangent of theta. That's going to be equal to the arctangent of negative 2 over 4. The arctangent and the tangent cancel each other out, leaving just the theta. And going to my calculator, trig, we want arctan, hopefully I'm in the right mode, of negative 2 over 4. And that gives me negative 26.6 degrees, which I believe it's down in the fourth quadrant there. Okay, so that is how we now have the entire thing. There's the direction, there's the magnitude. We've now described vector A completely. A couple of things you need to know before we go. When we're talking about direction, there is a convention. The convention is that we measure from the conventional positive x-axis around in an anti-clockwise direction. That is the positive direction. So here is 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360, and it goes round and round and round. But this way is negative. Clear that guy off. If we go around the other way, we're talking negative. So here's 0, here's negative 90 degrees, negative 180 degrees, negative 270 degrees. Anytime you are measuring conventional angle, you begin at the positive x-axis. Positive goes around anti-clockwise, negative goes around clockwise. Okay, a couple of other things. We can do math with vectors. And what is the result? Okay, if I want to know, say I have some vector, just go with my old standby here, there's vector A, once again making a comeback. Well, if I want to know twice vector A, now look at what this really means. This really means A plus A. If we look at what does multiplication mean, it's really just repeated addition. So I'm going to take vector A and add on to it vector A. So here's vector A, and I'm going to go ahead and just tag vector A on it again, meaning that, well, there's 2A. It's twice as long. Pretty straightforward. If you multiply a vector by what a number, just a number, this would be a scalar. Okay, so this is called scalar multiplication. Multiplying a vector by a scalar, it increases the length of the vector by the multiplier shown. Well, that's really interesting, but what happens if we do something like this? Well, what's minus 1A? Well, we're going to take A negative times. Negative 1 times. So if here's A, we need to take A negative 1 times. Remind us what this means in class. In physics class, the sign is always direction. This is just direction. So I'm going to take A, which was pointing off this way, and we're just going to flip it around. So if that's A, there's minus A. It just points in the exact opposite direction. So what we get here is that there's no such thing as subtraction. There's no subtraction. No subtraction. We just add the negative. Add the negative. That's all you want to do. No such thing as subtraction. We have addition, which is one vector followed by the next vector. The resultant vector would be here. That's A plus B. So we have addition. This is how you do it. You line it up head to tail. The resultant goes from tail to tail to head. So you get another vocabulary word here. This is the resultant vector. And that is the answer to a vector addition problem, is the resultant vector. Okay, there's another vocabulary concept that might come up while we're talking about vocabulary, and this is called resolving. If you hear the words resolving a vector, what that means is that we're going to break a vector into components. Okay, and then when you recombine components to get the original vector, well, that's the answer to an addition problem. You take component 1 plus component 2 to get a resultant vector. So there's those vocabulary words. Another idea that is important that you need to understand is equal vectors. Okay, so what does it mean for two vectors to be equal? Okay, the key to this is understanding that a vector has only two parts. It has a magnitude, that is how long is it, and it has a direction, that is at what angle does it point. Where the vector is located doesn't matter. So just because here vector A is in that spot and vector A is over here, as long as these two vectors have the same length and the same direction, they are equivalent. And that's all. If they are the same length and the same direction, they are equivalent. You can pick up a vector and place it anywhere you like in the whole world. Good. Another idea here. Looking back to remind us about this whole negation thing. So negative 1 times vector A is the opposite of vector A. So what we say here is this is sort of getting at a problem we have. We can have parallel lines, and we say, oh, well, their direction or whatever is the same. They're parallel to one another. Or we could have parallel vectors. They're headed in the same direction, but when we say parallel, we actually imply they're heading in the same direction. So if vector A, and we'll extend this one a little bit, and vector B are parallel, what we mean is that their angles are equivalent. Okay, so parallel means angles are the same. Okay, but what do we say when vector A is this way and vector B is going the opposite way? We can't just say parallel, even though that in our old understanding of parallel, we would say, yeah, these are parallel, they run along, they never intersect, they meet all of that requirements. This has more information because the direction matters. A is going up and to the right, B is going down and left. So what we have is a new idea, and the idea is anti-parallel. So they are parallel in the sense that they never intersect. They go on, they never intersect. However, they run in opposite directions. They are anti-parallel. So this is a good start on vectors. This ran a little longer than I wanted, but there's just a whole bunch of vocabulary, and then once we have that down, we can learn to do something with it. So watch this a couple of times, take careful notes so that you have all of these ideas down when we go to actually start working with vectors in a meaningful way.